Paul finished his PhD with someone I know pretty well, Tim Belsol, at George Mason. Actually, I don't even know when he finished, but relatively recently.
Just last summer.
Just this last summer. And then has since joined us. So very happy to have you here. Thank you very much. And I think today's going to be speaking to some of his real expertise on seasonal, subseasonal prediction, which grew out of your PhD work predominantly, right?
Yep.
Okay. Thanks, Paul.
Yeah, thank you. Yeah, so today I'll be talking about identifying new sources of subseasonal predictability. So this is going to be a summary of some of the results from my thesis. All right, so looking at subseasonal predictions, what are they? I thought it might be useful to go through things that we do know what they are and then compare and contrast them. So we know, everybody knows what weather predictions are. We predict daily or hourly values, and those tend to be good up to 7 to 10 days in advance. And weather predictions are limited by the chaos inherent in atmospheric predictions. And so on the other side of things, we have seasonal predictions. So you might hear somebody say something like, this upcoming spring is going to be warmer than average or wetter than average. And so seasonal predictions predict a whole season or perhaps monthly values of temperature or precipitation. And these are made up to 1 year in advance. And seasonal predictions are limited by our knowledge of the boundary conditions. And so in between weather and seasonal predictions are subseasonal predictions. So for subseasonal predictions, we predict 2-week means of temperature or precipitation, and those are made up to 6 weeks in advance, although more commonly it's up to 4 weeks in advance. And subseasonal predictions are limited by both the chaotic atmospheric conditions and boundary conditions. And so oftentimes when you look at a subseasonal prediction, it'll be talking about a prediction for weeks 1 to 2 and weeks 3 to 4. And so to just get you oriented, if a prediction was made, for example, on February 7th, this last Friday, the weeks 1 to 2 prediction would be valid for the 8th through the 21st, so these 2 weeks. And then the weeks 3 to 4 prediction would be valid from February 22nd through March 7th. So that's kind of what we're looking at in terms of what time frame we want to predict. And just for fun, I thought we would look at the current subseasonal forecast. So NOAA puts these out every week on Fridays. And so this one was just issued on February 7th. And this is the weeks 3 to 4 temperature outlook. And so, like I just showed in the last slide, it's valid from February 22nd through March 7th. So the whole 2-week period. And in this case, this one is a probabilistic forecast. And so it shows the chances that we're above or below normal, where above and below are in reference to a 20-year climatology. And so for the end of the month, looks like here in Wisconsin, we have a better than average chance that we're still going to be below average temperatures. So, bummer. So who benefits from making subseasonal predictions? Why do we care? So there are some areas that have been identified as potentially being able to benefit. And those include things like water management, agriculture, disaster preparedness, and health. And in fact, there have been some case studies, for stations across the world, where subseasonal predictions have been integrated into such things as public health, agriculture, water resource management, energy and utilities, and early warnings of extreme events. And so just for some examples of applications here in the U.S., in the western U.S., we can look at water management. And in particular, California relies on water reservoirs for agriculture and drinking water. But one of the difficulties that they have is that heavy rainfall events from atmospheric rivers provide up to half of California's annual precipitation. And so they have to have a balance between having enough water in the reservoirs and not flooding. And so subseasonal predictions of atmospheric rivers in particular can give reservoir managers the information to decide how to prepare. Do they drain off some of the water beforehand, or do they keep it? As a second example, extreme temperature events, both heat waves and cold spells, can be especially dangerous if they persist. And here in the mid-latitudes, these events can persist for 1 or 2 weeks. And so these temperature extremes lead to higher energy demands. And so if we can predict these extreme temperature events up to 3 or 4 weeks in advance, then power plants can do whatever it is that power plants do to prepare for this spike in energy. And just as one final example, we can look at false springs. So those are when a hard freeze occurs after plants have begun growing. And so if we can predict these events, then farmers can prepare for the freezing temperatures. So I hope that I've given you some examples and convinced you that these are actually good things to do. And so we want to know how good are subseasonal predictions. And so we have kind of, in a qualitative sense, the forecast skill going from 0 to excellent on the y-axis here, and then the forecast range on the x-axis going from 0 days out to full season here. And so we have weather forecasts starting at 0 to 1, 0 to 1 day in advance. Excellent skill, but then that drops down as we get to about 10 days. And then seasonal, out here in the purple, starts at fair, so they're okay at a month, and then those drop off over time as we get to the full season. But then we have subseasonal, or in this case it's called S2S, subseasonal to seasonal predictions. Those start at, ooh, that's not great, they start at poor, and then they drop down to 0. So that seems not promising, if the best we can do is poor. And so are subseasonal predictions really that bad on average? Kinda, but that comes with a caveat, that there are times when we know the skill of a forecast will be better. And so key to this are what we call sources of predictability. And so these are climate processes that both affect the temperature and are themselves predictable on subseasonal timescales. And so some of the known sources of subseasonal predictability include things like ENSO, and here ENSO is bolded because it is possibly the biggest source of subseasonal predictability. But there's also things like the Madden-Julian oscillation, atmospheric blocking events such as the NAO and PNA, the boreal summer interseasonal oscillation, or the BSISO, sudden stratospheric warming events, and surface soil moisture. So not all of these will be applicable at all times or in all locations, but these are just some of the sources that we can use that we know about the climate system to improve our subseasonal predictions. And so it's worth going into a little bit of detail on how we get predictability from these sources. And so, for example, if we look at ENSO, so this is a map of the temperature response to the positive phase of ENSO, or El Nino. And so in this map we can see that during an El Nino event, Alaska and Canada here have a positive temperature anomaly, while the southern US and eastern US have a negative temperature anomaly. But this explanation of predictability is a statistical one, in that this map is seasonal anomaly composites conditioned on the mean 3.4 index. So we know what El Nino is, and so we can use that information to get the statistics of the temperature response. But we don't know just statistics. We also know dynamics. We also know thermodynamics. So we have a physical reason to think that ENSO, which is a tropical Pacific phenomenon, is able to influence temperatures over the United States and North America and beyond. So we know that El Nino is a source of, or the heating in the tropics from El Nino is a source of convection, which can cause Rossby waves, and because of our knowledge of dynamics and because we know that the Earth is spinning, those Rossby waves propagate and they spin, and they impact the U.S. And so here in this map, we see that there's, if we're looking at 500 millibar height, we have a positive anomaly over Canada and a negative anomaly over the southern U.S. and eastern U.S. But this, even though we know the dynamics and the thermodynamics, this physical explanation is still based on what we know El Nino is. And in particular, this is seasonal anomaly composites, again, conditioned on the mean 3.4 index. And so, historically, when we look at sources of predictability, all of the sources of subseasonal predictability that we know about have been first identified, and then later their impacts are derived. And so it's worth asking then, if we first identify the predictability and then derive its impacts, have we found all of the sources of predictability? And so to answer this question, then we ask, how can we quantify predictability without reference to one of these mechanisms? And so to do this, to quantify predictability without reference to some climate mechanism, we can use this kind of conceptual idea that if we have some force in here that influences temperature at some time t, and then continues to influence temperature at some later time, t plus tau, then the structures of temperature at time t and t plus tau will have a correlation between them. And so if we can identify the structures of temperature that are correlated over time, in particular on subseasonal timescales, then we should be able to kind of back out of that what the forcing is. And in particular, our analysis, we want to be careful to make sure that we allow the flexibility that the predictable structure could change. So for example, if there's a wave propagating across the US, that's not going to look the same at time t and at time t plus tau. And so one caveat, of this way to quantify predictability is that we do know that there are forcings that evolve predictably, that those forcings do influence temperature at time, at only one time, say time t plus tau. But again, that would be starting with the forcing and then looking at its influence at some time. And so the way that we can identify correlated structures in temperature is by using canonical correlation analysis, or CCA. And so given vectors x and y, CCA will find a linear combination of x and a separate linear combination of y that maximizes the correlation between them. And so since using grid point data would lead to a nil-pose problem, x and y are the leading EOFs of temperature for my project. And so CCA is actually a standard method and is in fact almost 100 years old. And it has been used in climate studies, often to find relationships between two variables, with some examples of papers listed here. However, CCA as presented in standard statistics textbooks is effectively broken when you try to apply it to climate research. And it's broken in three ways. The first is that the user has to choose and justify the number of EOFs used for both x and y. Oftentimes, this is based on some percentage of total variance explained, which can actually differ wildly across studies. The second way that CCA is broken is that the significance test for the correlation is asymptotic, which is not ideal for small sample sizes. And when we're looking at subseasonal predictions, we don't have very many samples per season and don't have very much data. So we have small samples, and so that's not ideal. The third way that CCA is broken is that CCA maximizes the correlation between the temperature, temperature at time t and time t plus tau. And so like any statistical method that maximizes something, it will overfit, and so it will overestimate the in-sample correlation. This means that when you look at independent data, when you're verifying, the correlations are lower. And in fact, we would expect them to be lower than even the population correlation, so they're lower than the true correlation. And so we want to know how low is too low, and are these lower correlations consistent with the overfit correlation? And so to use an analogy, CCA in this way is kind of like a bike that's stuck in one gear. So it's okay if you just kind of want to putz around town, do some things that, if you aren't concerned about the number of EOS or you aren't concerned about the sample size. CCA can work for that. But as soon as you, encounter something, encounter a hill, it doesn't work so great. You have to make all these justifications for why you're doing what you're doing. It's not great. But fortunately, there are ways to fix your CCA bike. For the first problem, for choosing the number of EOFs, we can use an objective selection criteria. In this case, we used MIC, which was published in 2021, to determine the number of EOFs for both X and Y. For the second problem, for the asymptotic significance test, we can use a Monte Carlo difference-based significance test for the in-sample correlation. And so I didn't come up with either of those solutions, but I think that the work that I did for my thesis was the first time that those two have been used at least in the climate problems. And for the third one, for overfitting the in-sample correlation, I was actually able to develop a novel method to determine if the out-of-sample correlation is consistent with the measured correlation. And that actually comes with a second benefit, that it is able to constrain the range of the canonical correlation, at least for the leading mode. All right, so taking just a quick step back, my goals for my work and my research is to use CCA to identify correlated structures of temperature at subseasonal timescales, and then identify the source of the predictability. And so I actually did this in two ways in my thesis. I'm only going to show one using leg regression maps. And so going through just some of the data and the pre-processing that I did, the data that I used was the Era 40 reanalysis, which goes from 1957 to 2002, and I used 2 meter temperature, which is available on the daily. And then from those daily temperatures, I computed anomalies by removing the annual cycle, trend, and annual mean, and then convert those daily anomalies into 2-week means, so that they would be applicable for subseason. And then the EOFs are calculated from the 2-week means, and then apply CCA to all the seasons separately. But the rest of this talk will only focus on summer. And so, since we want to know the legged correlation and temperature, X and Y are both temperature over the US, with Y lagging X by some fixed value tau, where X and Y again are the 2-week means of the leading US of 2-week temperature. And so the values of tau that we looked at for each season, we looked at tau is 28 days, which corresponds to weeks 3-4, and then also tau is 14 days, corresponding to weeks 1-2. So we did those two separately. And it's worth reiterating too that X and Y are separate combinations of US, so they can be different patterns of temperature. And so we apply this, and we immediately run into a problem, and that problem is ENSO. I found that if you have a problem in your life, you can usually blame it on ENSO. So the problem specifically that we found is that the ENSO response dominates all the other predictable signals. So we ran CCA and we rediscovered ENSO. Like, that's not a great paper, not a great result. And so we want to remove ENSO from the temperature data before we find the predictability. And so since ENSO is largely seasonal, we can remove the seasonal mean from the temperature PCs prior to analysis. And so, for example, we removed the mean of summer 1957, and we removed the mean of summer 1958, et cetera, et cetera. And then we apply CCA to that data to find the leg correlations. Okay, so there are 3 main outputs that we're looking at when we look at CCA. So the first are the loading vectors. So those are the patterns of temperature. So we get 2 of them, one corresponding to the initial condition, X, here, and one corresponding to the response. In this case, we're looking, these outputs are for the leading weeks 3 to 4 mode in the summer. So we get 2 patterns of temperature. The variates then are the time series, and so to get the time evolution of the temperature, you know that at initial condition or at the response, you multiply the loading vector times the variate. And then the canonical correlation is the correlation between the X and the Y variate. In this case, including the uncertainties, the correlation is 0.19 to 0.31. So this being the leading mode represents the highest correlation in temperature that CCA was able to find in the data. And so looking at this correlation, this again kind of goes back to the idea that subseasonal predictions have a maximum skill of 4. That a correlation of 0.2 to 0.3 is not great. Like, it's not nothing, but it's also not great. But this is just the world that we live in. This is what we should expect. And so, just quickly, some results of applying CCA in general. I was able to identify significant modes in all seasons at both weeks 1, 2, and 3, 4. But the focus of this talk is the leading summer mode at weeks 3 to 4, as amplitude. So like I showed, this is the leading summer mode of weeks 3 to 4. So this panel on the left here is the initial condition temperature, and this panel on the right is the weeks 3 to 4 response temperature. So in the initial condition, we have mostly a positive anomaly over the U.S. With a negative temperature anomaly over Canada and like Washington State here. And then at weeks 3 to 4, we have negative temperature anomalies over the central U.S. and positive temperature anomalies over the western and eastern parts of the U.S. And so we want to know what the source is then of this mode, this correlation. And so we can look at lagged regression maps with 500 millibar height, and that will give us the evolution of height anomalies between the initial condition and the response. And then we can look at additional lagged regression maps as needed. So if it looks like there's something interesting from one part of the world, we can look at that. So looking at the lagged regression maps here, just to get you oriented, up here on the upper left is the lagged regression map, or the 500 millibar height regression map that's simultaneous with the initial condition. And then it moves forward in time, so this is 5 days after the initial condition, and 10 days, and 15 days, and so on, until down here at the bottom is the height pattern that's associated with the weeks 3 to 4 response. So at the initial condition here, we can see that there's a north to south gradient in height field over the U.S. That possibly could be coming from a wave here, and then that wave dissipates as we move forward in time at panel E and panel C here, and then as we start to look at 15 days, so panel D here, we start to see the beginnings of a wave that then grows in amplitude as we move forward until finally, simultaneous with the response, there's a very obvious wave that impacts the U.S. So in particular, something to note about this wave is that it's very zonally oriented, and so that fits well into descriptions of like a jet-trapped wave, or a certain global wave, it's been called. And so this wave appears to be coming from the Western Pacific here, in this little box that I've marked. And so then the next obvious variables to look at are precipitation and sea surface temperature. So we didn't find anything interesting with sea surface temperature, but we did with precipitation. So guess what? Here's some precipitation maps. And so again, these are in the same order as before. So with the initial condition here up on the upper left, and then moving forward in time until finally we get down to the simultaneous with the response here down at the bottom. And so we can see, so this box here is the same location as the box here in the 500 millibar height maps. And so we can see that there is in fact a large-scale precipitation anomaly here in the initial condition. That anomaly dissipates, as we go forward in time, 5 days, 10 days, and then starting in 15 days, there is another precipitation anomaly of the opposite sign that grows in amplitude until finally we are at simultaneous with the weeks 3 to 4 response here. And so, because this is in the same location that it looks like the waves, or the 500 millibar height wave is being generated, the consistency of these results suggests that precipitation in this location is the source of the leading weeks 3 to 4 mode. So there is, if you're not familiar with it, the boreal summer interseasonal oscillation is the summertime seasonality of the MJO. And that has, it's worth looking into to see if what we found is the boreal summer interseasonal oscillation. And so the BSISO here is characterized by large-scale convection that's propagating both northward and eastward over the Indian Ocean and the Western Pacific. However, there are some differences between the precipitation associated with this mode and the BSISO. In particular, the precipitation from this mode is further north than the BSISO indices typically indicate, and we don't see a large-scale precipitation anomaly with the opposite sign in my precipitation maps. And so to just compare them side by side, you can see that that in this regression with precipitation at the weeks 3 to 4 response, the precipitation anomaly is centered, around 20 north, whereas the BSISO indices only go up to 20 north. And we really don't see a corresponding large-scale negative precipitation anomaly in this regression plot, whereas we do in every single one of these on the right. And so this leads us to conclude that at the very least it's not the conventional BSISO. It would certainly be worth looking into the dynamics of BSISO and to see if what we found is related to it somehow. But just by looking at leg regression maps, this is really as far as we can go. Okay, so that's all for the weeks 3 to 4 mode. I do want to talk about our leading weeks 1 to 2 mode that we found in the summer. And so part of the reason that I want to talk about this mode is that this leading weeks 1 to 2 mode does seem related to the weeks 3 to 4 mode, but I'll get to that in a minute. So the loading vectors here, the temperature patterns, in the initial condition, we see some positive anomalies on the west coast, whereas the rest of the U.S. is negative anomaly. And at the weeks 1 to 2 response, we see a lesser amplitude negative anomaly over much of the south and west U.S., with perhaps a slight positive anomaly over the northeast. The correlation between the initial condition and the response is 0.3 to 0.5 or so, which is much better than what we saw before, but this is also looking at a much closer time scale, so we would expect a larger correlation. And so, without going into details, we found that soil moisture plays a role in this mode. And so we can look at the leg regression map, although that doesn't really change structure with time. It does change amplitude a little bit. So if we look at we can look at just one panel of the soil moisture regression map here on the left. And so in particular, there are two regions that I want to highlight. One is this positive anomaly soil moisture over the Great Plains, so that's wet soil, and then a negative soil moisture anomaly over the northwest U.S., so that's dry soil. And in those locations, when we look at the temperature, initial condition here on the left, and weeks 1 to 2 response on the right, it's in those locations that the temperature persists, whereas in the rest of the U.S., the temperature either flips sign or in the northeast here just kind of goes down to 0 anomaly or so. And so this suggests that there's atmospheric response going on as well as the soil moisture. And so we can look again at regression maps of 500 milliliter height. Again, this is the same orientation as what I had shown before, so simultaneous with the initial condition on the upper left here, and then moving forward in time, 5 days here on the right, 10 days after the initial condition here on the bottom left, and then finally simultaneous with the response here on the bottom right. And so we can see at the initial condition that we have, again, a zonal-oriented or a jet-trapped wave at the initial condition. This seems to be originating from the Western Pacific, that then degrades over time a little bit and then becomes, transitions to another wave here at the weeks 1 to 2 response. And so then, like before, the next thing to check is tropical precipitation. And so, indeed, we do find another large-scale anomaly precipitation in the initial condition, which then propagates a little bit to the west and dissipates somewhat by the time we get to the weeks 1 to 2 response. And so from this, we can conclude that the leading weeks 1 to 2 mode is related to anomalous soil moisture as well as a Rodney wave initiated by Western Pacific precipitation. And so the connection between the weeks 3 to 4 mode and the weeks 1 to 2 mode can be seen by looking at the weeks 3 to 4 response, particularly in 500 milliliter height precipitation, and comparing that to the weeks 1 to 2 initial condition. Again, 500 milliliter height here on top and precipitation here on the bottom. And so in both cases, we see that there is a zonally oriented Rodney wave that is also associated with this positive precipitation. Positive precipitation in the Western Pacific. And so this suggests that if we put these together, because this is the end of the weeks 3 to 4 mode, and the beginnings of the weeks 1 to 2 mode, this suggests if we smush them together in time, that we could come up with a big weeks 5 to 6 mode. So we haven't done that in CCA. This was enough. But this suggests that that further research could be interesting here. And so, in conclusion, we identified predictable modes at weeks 1 to 2 and 3 to 4 in all seasons. I presented the results from 2 of the summer modes. The leading weeks 3 to 4 summer mode was associated with Western Pacific precipitation, and the leading weeks 1 to 2 summer mode was associated with soil moisture and Western Pacific precipitation. And like I said, this weeks 1 to 2 mode seems related to the leading weeks 3 to 4 mode. And so I would be happy to take questions at this point.
All right, that's great. Any questions for Paul?
I have two questions. The first one, it sounded like you were always correlating the principal mode at the initial time and then the response time. Did you look at whether there could be correlations between principal, the leading mode, and some of the other ones that still had significant variance?
So looking at so if I found multiple modes in the season, if
It
there's...
sounded like you were doing correlations of EOS,
Yeah.
the initial time at the response time, but it was always the leading EOS. Did you look at correlations between like the leading at the initial time and the second EOS?
So I used a linear combination of EOFs. So in this case, I think it was like the leading, or at the initial condition, I think it was like 5 or 6 EOFs, a linear combination of those, and then like 6 or 7 EOFs, a linear combination of those for the Y.
My second question is interesting to show that there might be a link between this week 3 to 4 response and the initial conditions for week 1 to 2. And I understand this is all statistical, but wouldn't you think that there should be some consistency between the week 1 to 2 behavior that you get and the first part of the week 3 to 4? You know, you kind of showed.
Yeah.
And they start, the initial condition for week 3 to 4 was totally different than the initial condition for week 1 to 2.
Yeah, I think we would say then that that the weeks 1 to 2 mode doesn't persist for longer than that 2 weeks. So it doesn't give you predictability over the next 2 weeks.
Okay.
Of course,
So it might exist there, but it doesn't show up as correlated with that week 3 to 4.
Yeah.
Gotcha. Thank you.
Paul, with all of these correlations you use in this analysis, how much are they affected by climate change? Should we expect them to continue throughout the past as well as the present and future?
That would certainly be something interesting to look at. So I detrended all of the data, so I cannot answer that question. I do not know.
I guess following on Brad's question, the second CCA mode, you look at the second CCA mode at all, or just the first CCA mode?
I did, yeah. So in the summer for weeks 3 to 4, I think there were 4 significant modes. So just for this talk, I just presented the first one.
Did they all have that high wave number? I'm surprised to see the large, like the high wave number response in the mid-latitudes. I guess I think of those high wave numbers as probably being relatively fast, and so not tending to see that kind of large wave number response on longer time scales, like 2 weeks.
So I would have to look back in the results, but I think this was the only one that was associated with that high wave number from the Western Pacific. The other ones were, I think like there was some response from the PNA and the NAO, but this was just the most predictable.
And sorry, just one last question, and I'm sorry if I missed that earlier on, but the data you're using for CCA, that's like a 1 week average, or is it just daily data, or what's the,
It's a 2-week average.
a 2 week average?
Yeah.
Wow, just look at that high wave number of response.
Yeah.
Interesting.
Yeah.
So I realize some of this is not a data sampling problem, but you don't want to reduce your data any more than you have to. So when you're doing summertime, it's June, July, August,
Yep.
right? If you were able to split it though, and look at, say, first half of the summer versus second half of the summer, do you think it would be much different? You know, how similar are the patterns, let's say, all across the summer? And I guess that's different for temperature and precipitation maybe, but you might expect something different in the first half of summer than the
Yeah.
second half for precipitation.
Yeah, this is true. I don't specifically remember for this mode, but there was some analyses that we did that, I mean, because you can look at the time series of the modes.
Right.
And there were some that we looked at that really like only showed up in the second half of whatever season it was. So I don't know if we would want to like split it up and do CCA like that, but we could definitely look at the time series and do some analysis there. So I don't know about that one in particular, I'm sorry.
No, it's okay. More questions for Paul? Okay, well, let's thank him again. Appreciate it.